Assalamualaikum dan selamat sejahtera. My name is Siti Nursaheera. This project title is Projectile Motion was part of the dynamics and mechanics of machine course and was complete by group consisting of Aisyah Inshira, Nur Adriana Nadira, Nur Nadira Hana, and the last one is me, Siti Nursaheera. Of contents, we have 5 contents. First, introduction. Second, mechanism. Third, conclusion. And then discussion. The last one is conclusion. First content, it is introduction. This project involved designing a catapult to launch a ping pong ball exactly 1 meter using principle of dynamic and mechanics to calculate the necessary launch speed, angle, and spring stiffness. By applying reverse engineering, the team refined the design based on the test results. The experience enhanced understanding of real-world physics, highlight the importance of precise calculations in mechanical design, and promoted problem solving, teamwork, and practical engineering skills.
Hi, my name is Aisyah Inshira. I will continue the slide by explaining about the mechanism. So the mechanism is the launching mechanism operates by utilizing a spring compressed by 0.029 meter to propel a 0.027 kg ping pong ball at an assumed launch angle of 31.5 degree. So the ball is released from initial height of the 0.095 and travels a horizontal distance of 1 meter to reach a target located 0.095 below the launch point. So the motion of the ball is governed by a projectile dynamic under constant gravitational acceleration that is 9.81 meter over second square, enabling the prediction and control of the launch trajectory. I will explain about the calculation. So the first step is we must calculate the required initial launch velocity, that is VO. So how to find VO? We use a y-axis and x-axis to find it. By using that, by using the formula x equal to xo plus VOT plus 1/2 GT square, we can substitute both axes equation to get a value of t. So from the substitution, we can get the VO, that is 4.15 meter per second. So next, we calculate the time. How to calculate the time? We use x-axis equation, that is t equal to 1/0.853 VO. We just put the VO that we get 4.15 in the formula, and then we calculate the spring stiffness by using a formula 1/2 k x square equal to 1/2 mass initial velocity square. So we have a data, all of it, but we don't have k. So the k is a string stiffness. After calculate, we can get 55.23 Newton per meter. Thank you. That's all from me.
So, from this task, we create a basic spring-powered catapult to launch a ping pong ball 1 meter to hit target from a height of 0.09 meters. We calculate the needed launch velocity and compute the spring stiffness. We begin by calculating how long it would take for the ball to fall using basic kinematic equation. Next, we determine the initial horizontal distance. After that, we using the energy conversion from the ball's kinetic energy to the spring's potential energy. These steps help us understand the link between force, motion, and energy. Choosing the right launch angle was one of the hardest parts. We assumed 31.5 degrees was a good angle for short distance projectile motion. To make the calculation easier, we ignore air resistance since it would only have a small effect in real life. This made it easier to focus on the basic physics. Overall, we gained a greater knowledge of how class theories apply to real mechanical systems to the computation and design process, especially in dynamic motion and spring mechanics. That's all from me. Thank you.
In conclusion, the assignment demonstrates how basic ideas from the dynamic and mechanics of machine, such as particle kinematic and kinetic and energy conversion principle, may be applied in a real-world situation, along with recognizing the limitation of idealized models and the influence of a real-world factor like air resistance and material qualities. It also emphasized the significance of critically debating conclusion and analyzing the working process. In the end, this project was a useful exercise in applying engineering principles to theoretical mechanical concepts. Thank you.